Okay, I'm now going to work 2008. Let's see where I am. Oops, I'm holding my thing upside down. Sorry, guys. Okay, so I need to grab a pen. Let's go. I have no blue. Okay, so this is 2008, uh, Form B, question one. And you'll notice as you're working these old problems that the first problem was always equilibrium, always. So coming down here, answer the following questions regarding the decomposition of arsenic pentafluorides. Remember, decomposition is one thing, breaks into two. And so we have a 55.8 gram sample of arsenic fluoride, and it's introduced to a 10.5 liter container at 105 degrees. What is the initial molar concentration? So coming back, A and then I or 1. Remember now molarity is moles per liter. That's the unit. And so they gave us 55.85 grams. And again, when in doubt, go to the mole. So if you add 1 arsenic and 5 fluorine, what is arsenic? Arsenic is 74.92 plus 5 times 19. And if you do that, you get the molar mass, which is, what did I get when I did that? 169.92 grams per mole. And again, when in doubt, go to the mole. So 162.92 grams in a mole. And if I pause to do that on my calculator, should have done this ahead of time, 55.85 divided by 169.92, I get 0.329 moles of this, but they didn't ask for that. They asked for molarity. So now molarity is moles per liter. So we have 0.329 moles. And then they said we had 10.5 liter container. And if I do that, 0.329 divided by 10.5, you get 0.313 molar. And that's good. And you're going to notice that we're going to use that number gets used over and over again. So, okay, new page. So then I and A asked for, sorry, A and now I says, what is the initial pressure in atmospheres of the AS5 in the flask? Again, they love gas laws, particularly this one, PV equals nRT, but they want to know the pressure, so we're solving for P. So the first thing we need to do is divide both sides by V to isolate it. And so P is equal to nRT over V. And we just did this. I'm going to go back. N was 0.329 moles. So we don't want to reinvent the wheel. So N is 0.329 moles. R is 0.08206 atmospheres times liters per mole K. And then it is said that the temperature was 105 K, which is, sorry, 105 degrees Celsius. So we have 105 degrees Celsius plus 273, 873. So that's 378 K. So 378 K. And then volume is downstairs. So I have to do the reciprocal 1 over 10.5 liters. And Mole cancels with mole, and K cancels with K, and liters cancels with liters, and nothing cancels with atmospheres, which is great because that's what we're looking for. And I get that it is 0.971 atmospheres. Now, the one thing I have to say is when I check the scoring guidelines have 0.969 atmospheres, which is very close. And in 2008, the value of R on the formula sheet was 0.0821. But now, in the new test, it's 0.08206. And this slight difference is what's causing my answer to be different than the answer on the scoring guidelines. It's just because um, they changed the value of R. All right, so new page. So then B is, let's go back and just read it together. In terms of molar concentrations, write the equilibrium constant for the decomposition. So using this reaction, write the expression for Kc. So again, they have ASF5. Notice they always give you physical states in equilibrium because solids and pure liquids don't go in the equilibrium constant, but these are all gases. And so Kc is the concentration of the AF3 to the first power times the concentration of fluorine to the first power over the concentration of AF5 to the first power. And that's B. In terms of molar concentrations, write the equilibrium constant expression for the decomposition of this. All right, C. Again, I don't think that you need to do an ice chart, but I love ice charts, so I'm going to go nice and slow. ASF 5G goes to ASF3 G plus F2 gas, and then ICE. And because this is a concentration, this is a molarity, not an atmosphere. And the thing that's really cool about this problem is we just solved for this in A, so that we know the initial concentration of this is 0.0313, and this is 0, and this is 0. And the interesting thing is they say that 27.7% of the ASF5, now I'm doing CI, when equilibrium is established, 27.7% of the original number of moles of AF5 have decomposed. So I'm going to take 0.277 times 0.0313 molar. And when I do that, I get, what did I get when I did that? I don't even know where I wrote that down. Oh, yes, I did. This answer ends up being 0.00867. So that means 27.7 of this goes away. Sorry, 0.867. And because of the 1:1 to 1 mole ratio, that means 27.7 of this comes up. And remember, this third row is gotten by adding. So 0 plus 0.00867. This is 0.00867. Now I got this weird sig fig rule. When I do this on the calculator, just like a 7th grader would do it, 0.0313 minus 0.00867, I get 0.2263. But remember the rule for subtraction. So this one has 4 decimal places, but this one has 5. So I only get 4. So the best answer here is 0.0226. Now, what's the question? Calculate the molar concentration of ASF5 at equilibrium. So I'm going to just go over here just a tad, and the answer is this. So the concentration of AsF5 at equilibrium is 0.0226 molar. All right, new slide. And then, so this is CII. And it says, using molar concentrations, calculate the value of the equilibrium constant. So now I got to go back just to show you that we're going to put this in, and this in, and this in. So I think this is forward. Oops. Where did I do that? All right, so remember that this is the concentration of AF3 times the concentration of F2 over the concentration of AsF5. And so this is 0.00867 times 0.00867 divided by 0.0226. And if I do that, I don't think I ever wrote that down. Oh, yeah, I did. I get 0.00333 because this has 3 sig figs, this has 3 sig figs, and this has 3 sig figs. Okay, moving right along. Last one. Calculate the mole fraction of the fluorine. So what is the mole fraction of the fluorine? There's a number of ways to do this, but you have to realize that in equilibrium, everything's in the same container. And so mole fraction is actually the number of moles of, so the formula is, it would be moles of fluorine over the moles of fluorine plus the moles of AsF3 plus the moles of AsF5, because mole fraction is, if you want the mole fraction of fluorine, it's the moles of fluorine over all the moles. If you wanted the mole fraction of arsenic trifluoride, it'd be the moles of arsenic trifluoride over all the moles. But because we know the molarities, but it's in a 10.5 liter flask, and all of these would be divided by 10.5, and it would be proportional. I think that the easiest way to do this problem is just go 0.00867. That's the molarity of the fluorine over 0.00867 plus 0.00867 plus 0.0226. And if you do that all together, you will get, I think I did that on the back, you will get 0.217. Now, I just want to show you an alternate approach, which I think is way more work. But if you go sorry, I don't know what I did. I don't want to do that. Another way to do it is, if you have 0.00867 moles per liter, because that's what molarity means, times 10.5 liters, this cancels this, and so you would end up with 0.0910 moles of both F2 and AsF3, because they're the same if you look at the ice chart. And then if we go 0.0226 moles per liter, and then go times 10.5 liters, and then this cancels this, and you end up with 0.237 moles of AsF5. And now if you do the mole fraction of fluorine, you end up with 0.0910 moles. Notice that everything's going to cancel over 0.0910 moles plus 0.0910 moles plus 0.237 moles. And if you do that, you also get 0.217 because you have a 10.5 in the bottom up here and all down here. And so if they're all in the same container, the molarity and the number of moles are it's proportional, and you get the same answer either way. So I would do it the easier way. Okay, that's it.